Light is a universal language. It doesn't care about borders or languages. It speaks a math language that everyone can understand. And this makes it the perfect messenger to send out into the cosmos in search of knowledge. Light also travels fast, like really fast. And this makes it the perfect messenger to send out into the cosmos, because it can bring back knowledge from very far away places before it's too late. Every time we look up at the night sky, we are not seeing the universe as it is now. We are seeing it as it once was. The light from the moon takes just over 1 second to reach us. Sunlight about 8 minutes. The glow of the Andromeda galaxy arrives after a journey of more than 2 million years, and the faintest smudges captured by our most powerful telescopes carry messages across more than 13 billion years of cosmic history. Every photon, every particle of light is a time traveler, a messenger from the past. To study the universe is to study light. Through it, astronomers reconstruct the story of everything, from the moment the cosmos first became transparent to the birth of stars, and galaxies, and black holes, to the intricate physics that shapes our own planet. In other words, light is how we measure the universe. Without it, we would be lost. Now here's the kicker. This works both ways. Not only does light allow us to measure the universe, but the universe also tells us about itself through light. By studying the light from distant stars and galaxies, we can learn about their atmospheres, their chemical activity, and even their magnetic fields. In a way, the universe is speaking to us through light, and all we have to do is listen. Let us take a journey back in time with our cosmic messenger and explore the incredible power of light as a time machine. Imagine you're standing on a beach at sunset, watching the fiery ball of the sun sink below the horizon. You might think the sky is on fire. But what you're really seeing is the light from the sun bouncing off the clouds in the atmosphere. The reason why the sky is blue during the day is because the molecules in the atmosphere absorb and scatter the shorter wavelengths of light, like blue and violet, while the longer wavelengths like red and orange pass through the atmosphere more easily. This is why the sky is blue during the day and red at sunset. But it's not just the color of light that changes. The brightness also changes depending on the angle of the sun. This is because of a phenomenon called inverse square law. The brightness of an object is inversely proportional to the square of the distance between the object and the observer. As the sun sets, it appears more red and dimmer because it is farther away from the Earth than it was when it was higher in the sky. When light passes through different mediums, it can also change direction. This is called refraction. When light passes from one medium to another, like from air to water, it bends because the speed of light is different in different mediums. Refraction is what causes the sun to appear distorted when it's near the horizon, and it is also what causes mirages in the desert. Light can also be polarized, meaning that the waves of light oscillate in more than one plane. When light is polarized, it can be blocked by certain materials. This is called polarization. Polarization filters only let light waves that are oscillating in one plane pass through. Polarization is what allows us to reduce glare from our sunglasses, and it's also what is responsible for the beautiful colors we see in a polarizing filter. As our cosmic messenger continues its journey through space, it carries with it the information we need to understand the universe around us. By listening to the language of light, we can unlock the secrets of the cosmos and learn about our place in it. So next time you see a beam of light, remember that it's not just a ray of sunshine. It's a message from the past, a story from the universe. It's a story that has been billions of years in the making, and it is a story that is still being written. You know, there's so much more to light than meets the eye. Like, did you know that light can actually bend around corners? It's true. It's called diffraction, and it's what allows us to see things like rainbows and the rings around a CD. Or did you know that light can interfere with itself? It's called interference, and it's what creates the beautiful patterns we see in soap bubbles and oil slicks. Light is truly an amazing phenomenon, and we've only scratched the surface here. But hopefully this gives you a new way to appreciate the world around you and the incredible power of light. It's 1964, and the world is on the brink of a revolution. The Beatles are topping the charts. Space travel is captivating the public imagination. And something extraordinary is about to happen that will change our understanding of the universe forever. On April, something extraordinary happened. Two engineers working at Bell Telephone Laboratories in New Jersey stumbled upon a mysterious hum coming from the antenna of their satellite communication system. At first, they thought it might be interference or even space junk. But what they discovered would turn out to be much more profound. What they tuned in was a signal so unexpected, it defied explanation. It was a nearly uniform glow coming from every corner of the sky. Arno Penzias and Robert Wilson had just detected the cosmic microwave background radiation, the echo of the Big Bang, the oldest light in the universe. This discovery, which earned them the Nobel Prize in Physics in 1978, opened a window into the history of our universe. It showed that the universe was once incredibly hot and dense, and that it has expanded over time. It also provided strong evidence for the Big Bang theory, the prevailing cosmological model for the universe. But this was just the beginning. The detection of the CMB led to a series of groundbreaking discoveries that continue to shape our understanding of the universe today. But before we delve into the amazing stories that unfolded, let's take a moment to appreciate the incredible journey of this ancient light. The cosmic microwave background radiation is a remnant of the intense energy that filled the universe in the moments following the Big Bang. In the early universe, the cosmos was a sea of particles moving at unimaginable speeds. As the universe expanded, these particles began to cool, and the energy transformed into electromagnetic radiation. Eventually, the radiation decoupled from matter, meaning it was no longer being absorbed or scattered by particles. This ancient light has been traveling through space for billions of years, carrying with it a wealth of information about the early universe. The fact that we can still detect this faint glow today is a testament to the incredible power and reach of light. It is a reminder that the universe is full of wonders, and that we are privileged to be able to explore it in such detail. Now, let's dive into the amazing stories that unfolded after the discovery of the cosmic microwave background. One of the first remarkable stories to unfold after the discovery of the cosmic microwave background is the tale of John Mather and George Smoot. In the late 1980s and early 1990s, these two scientists led a mission called COBE, the Cosmic Background Explorer. Their mission had a simple yet ambitious goal: to measure the temperature of the cosmic microwave background radiation with unprecedented accuracy. COBE's measurements provided the first detailed map of the CMB and revealed some surprising findings. One of the most significant discoveries made by COBU was the existence of anisotropies in the CMB. These are tiny variations in temperature across the sky. Although each part of the CMB is only a few millionths of a degree warmer or colder than the average, they provide an important clue about the origin and evolution of the universe. Smoot and Mather's work on COBE earned them the Nobel Prize in Physics in 2006, cementing their place in history as pioneers of modern cosmology. But their work was far from over. After COBE, Mather and his team set their sights on an even more ambitious goal: measuring the polarization of the CMB. This information could shed light on the nature of the universe. As earliest moments, and help solve some of the biggest mysteries in cosmology, such as the identity of dark matter and the role of inflation in the early universe. Mather and his colleagues launched the Wilkinson Microwave Anisotropy Probe, or WMAP, in 2001 to study the CMB polarization. WMAP provided an even more precise map of the CMB and confirmed the predictions of the Big Bang model. It also provided evidence for the inflationary theory of the universe, which suggests that the universe went through a period of rapid expansion in the first few milliseconds after the Big Bang. WMAP also helped to refine measurements of the age, shape, and composition of the universe. The mission was a huge success, and it cemented NASA's reputation as a leader in space exploration and scientific discovery. Meanwhile, back on Earth, cosmologists were analyzing the data from WMAP and making some fascinating discoveries. One of the most exciting developments was the confirmation of the inflationary theory. This theory had been proposed in the 1980s as a way to explain some of the features of the cosmic microwave background. It suggested that the universe had gone through a period of extremely rapid expansion in the first few milliseconds after the Big Bang. This expansion would have smoothed out the universe, making it more uniform than would have been possible under the Big Bang theory alone. The confirmation of inflation was a major breakthrough for cosmology. It provided strong support for the idea that the universe was created in a hot, dense state and then expanded rapidly, eventually cooling and forming the structures we see today. But the story doesn't end there. The same scientists who confirmed inflation went on to make even more remarkable discoveries. In 2013, they announced that they had found evidence for a period of reionization in the early universe. This was a time when the universe was filled with a dense fog of hydrogen gas. But as the first stars and galaxies formed, they emitted ultraviolet radiation that ionized the hydrogen, clearing the fog and allowing light to travel more freely. This discovery was another piece of the puzzle in understanding the evolution of the universe. It showed that the early universe was not static, but was full of dramatic changes that shaped the cosmos as we know it today. The legacy of COBE, WMAP, and the scientists who worked on these missions continued to inspire and amaze. Their discoveries have revolutionized our understanding of the universe and have paved the way for future missions such as the James Webb Space Telescope. As we continue to explore the cosmos, we can be inspired by the courage, curiosity, and dedication of those who came before us and push the boundaries of human knowledge even further. As the work on WMAP was coming to an end, a new mission was just beginning. The European Space Agency launched the Planck spacecraft in 2009 on a mission to create the most accurate map of the CMB ever. Planck measured the temperature of the CMB with incredible precision, confirming many of the predictions of the Big Bang model. It also provided evidence for the theory of inflation and helped to refine measurements of the age, shape, and composition of the universe. Planck also studied the polarization of the CMB, providing clues about the physics of the early universe and the nature of dark matter. The mission's data was so rich that scientists are still analyzing it today and making new discoveries. But Planck's work was not without its challenges. One of the main difficulties faced by the Planck mission was the contamination of the CMB by dust and gas in our own galaxy. This can obscure the view of the distant universe and make it difficult to study the CMB. Planck scientists developed sophisticated methods to remove this contamination and reveal the pristine signal of the CMB. Another challenge was the analysis of the enormous amount of data collected by the spacecraft. The Planck mission collected more than 1 terabyte of data, equivalent to about 1 million gigabytes. This data had to be analyzed and processed to create the final maps and models of the CMB. Scientists used supercomputers and advanced algorithms to sift through the data and extract the most accurate signal possible. Despite these challenges, the Planck mission was a resounding success. The spacecraft's instruments worked flawlessly, and the data collected was of exceptional quality. The final maps and models created by the Planck team are among the most detailed and accurate ever made and have provided an invaluable resource for cosmologists around the world. As we look to the future of cosmology, we can be inspired by the incredible achievements of the Planck mission and the other scientists who have come before us. Their dedication, hard work, and perseverance in the face of adversity have pushed the boundaries of human knowledge and revealed the secrets of the universe to us. And now the baton has been passed to the next generation of space telescopes, including the James Webb, equipped with cutting-edge technology and advanced scientific instruments. These new telescopes promise to take our understanding of the universe to new heights. They will continue the legacy of discovery and exploration that has been passed down from one generation of scientists to the next and will undoubtedly lead to new and exciting discoveries in the years to come. The story of light reveals the interconnectedness of everything in the universe. We are literally made of starlight. The atoms that compose us were forged in the cores of long-dead stars. The energy from those stars ultimately driving the chemical reactions that sustain life on Earth. The story of light is a story of connection, a reminder that we are all part of something much larger than ourselves. It is a story that inspires awe and wonder and reminds us of the importance of exploring the universe and understanding our place in it. So the next time you look up at the night sky, remember that you are seeing not just stars and planets, but the echoes of the Big Bang, the whispers of ancient stars, and the light that connects us all. When we think of the universe, we tend to imagine silent, unending darkness, punctuated only by pinpricks of starlight. But this couldn't be further from the truth. There is a cacophony of light all around us, and it's telling a story written in every color of the rainbow. Now, once the universe lit up with the first stars and galaxies, photons began to tell new and extraordinary stories. Among the countless sources of light in the cosmos, some stand out as cosmic beacons. Objects so luminous, so powerful, that they illuminate not only themselves, but the very structure of the universe around them. 3 of these stand above the rest: quasars, gamma, bursts, and gravitational lensing. Each, in its own way, is a natural telescope into deep time. In 1963, astronomers detected a puzzling radio source, later identified with a faint star-like object. But when its spectrum was analyzed, the emission lines made no sense, until it was realized that the object was so distant that its light had been stretched, or redshifted, by billions of years of cosmic expansion. This was the first quasar, short for quasar-stellar radio source. Quasars are not stars at all, but the blazing centers of young galaxies, powered by supermassive black holes, devouring matter at furious rates. As gas and dust spiral into these black holes, they form an accretion disk that can shine brighter than an entire galaxy. Some quasars release energy equivalent to trillions of suns, visible across billions of light years. A typical quasar shines about 10 times as brightly as an entire galaxy. The name quasar was coined because many of the first ones discovered were thought to be quasistars. Only later did we realize they were extremely energetic, active galactic nuclei. This realization changed how we understand the evolution of galaxies. Originally, astronomers believed that quasars were a special class of galactic nuclei. However, further research showed that they are just a more active version of what we see in the center of most galaxies today, including our Milky Way, just in a more evolved stage. In fact, quasars are like galaxies on steroids, with much higher rates of star formation and activity in their central regions. The huge black holes at the heart of quasars are thought to play a crucial role in regulating the star formation in their host galaxies. Quasars get their energy from the accretion of matter onto these black holes. As matter falls onto the black hole, it forms a swirling disk and heats up to millions of degrees. This hot gas emits light across the electromagnetic spectrum, from radio waves to X-rays. What makes quasars so valuable as cosmic time machines is their reach. They are among the brightest objects in the universe, allowing us to study conditions at epochs less than 1 billion years after the Big Bang. Their light carries fingerprints of the gas it passed through: hydrogen clouds, intergalactic filaments, and the early chemical enrichment of the cosmos. In essence, quasars serve as flashlights shining through the fog of the young universe, revealing structures otherwise invisible. Quasars are the long-burning lighthouses of the early universe. Gamma ray bursts, or GRBS, are its sudden flares, brilliant, short-lived, and violent. First detected by military satellites in the late 1960s, GRBS puzzled astronomers for decades. These bursts release in seconds more energy than our sun will emit in its entire 10 billion year lifetime. Today we know they are caused by catastrophic cosmic events, the collapse of massive stars into black holes, or the collision of neutron stars. There are 2 main classes: long-duration GRBs, typically linked to hypernovae, the explosive deaths of massive stars. Short-duration GRBs, produced when 2 neutron stars spiral together and merge. Both unleash intense gamma radiation, followed by afterglows across the electromagnetic spectrum. While gamma-ray bursts are rare, they offer an unparalleled view of the most violent phenomena in the universe. During a long-duration GRB, a massive star several times larger than our sun collapses at the end of its life. The collapse forms a core of either a neutron star or a black hole surrounded by a massive envelope of hot gas. As the collapsed core rapidly spins, it drags the surrounding gas inward, accelerating it to extreme speeds. This forms a powerful jet that blasts away from the collapsing star, plowing through the outer layers of the star and punching a hole through the stellar envelope. This process accelerates particles too near the speed of light, which emits gamma rays as it slows down. BRBs are brief but brilliant. The total energy released during a GRB can reach 10 to the 54th power ergs. For comparison, the total energy output of the entire Milky Way galaxy is only about 10 to the 37th power ergs per second. After the initial gamma ray burst, the hot material surrounding the collapsed core continues to emit radiation across the electromagnetic spectrum, giving rise to an afterglow that can last for weeks, months, or even years. This afterglow is emitted as the fast-moving material from the jet slams into the surrounding medium, which could be the stellar wind of the massive star or the circumstellar medium. The short-duration GRBs are produced when two highly magnetized objects such as neutron stars or a neutron star and a black hole merge. As the two objects spiral towards each other, they emit a tremendous amount of gravitational radiation, which causes them to lose energy and eventually merge. During the merger, the strong gravitational fields involved produce a fireball of gamma rays. In both cases, the jets produced by these explosions accelerate protons and heavier nuclei to very high energies, producing a cascade of lighter particles and photons. These particles collide with the surrounding medium, emitting radiation that can be detected across the electromagnetic spectrum. Why do they matter for our story of light? Because they are so bright that they can be seen across nearly the entire observable universe. The farthest GRB detected so far comes from a time less than 600 million years after the Big Bang. These bursts allow astronomers to probe conditions in the early cosmos, mapping the distribution of matter and the history of star formation. Like cosmic flares fired across time, GRBs are both warnings and guides, rare events that briefly outshine everything else in the sky. So far, we've seen two sources of light from the early universe: quasars and GRBs. They are the universe's fire beacons, burning brightly to illuminate the darkness. But our story would be incomplete without mentioning the universe's magnifying glass: gravitational lensing. We have come now to one of the most remarkable features of the cosmos, a cosmic quirk that turns the very structure of space-time into a lens. Bending and focusing the light from distant worlds. This is gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. Massive objects distort the fabric of space-time, warping the path of light that ventures too close. When light from a background galaxy or quasar passes by a massive object like a galaxy cluster, it is bent and magnified, creating a distorted or even multiple images of the source. It's as if you were looking at a spoon and a glass of water, and it appeared to be bent or broken. This happens because the spoon is actually being seen through a layer of water which has a different density than air. This change in density causes the light rays coming from the spoon to bend, making it look like it's in a different place than it really is. Similarly, in space, the light from a distant galaxy is bent by the gravitational field of a massive object like a galaxy cluster. This bending of light can cause the distant galaxy to appear distorted, or even split into multiple images. Gravitational lensing has become one of the most powerful tools in modern cosmology. It allows astronomers to magnify distant galaxies, making it possible to study objects too faint to see otherwise. The magnification can be so great that it reveals details such as the structure of a galaxy S-bulge, and disk, and even the motions of individual stars within it. Moreover, gravitational lensing can also be used to detect dark matter. Since the amount of bending observed in a galaxy cluster can tell us how much mass is present, if the amount of bending is greater than expected based on the amount of visible matter in the cluster, then there must be an additional amount of dark matter present. Finally, gravitational lensing can also be used to peer deeper into time. By using a massive galaxy as a natural telescope, astronomers can observe light from some of the earliest galaxies in the universe. This is because the massive galaxy distorts the light from the background galaxies, making them appear closer and brighter than they would otherwise seem. This means that astronomers can use gravitational lensing to see galaxies that are much farther away than they would otherwise be able to detect. One of the most famous examples of gravitational lensing is the Einstein cross, where the light from a single quasar is bent around a foreground galaxy into 4 distinct images. There are also other cases where gravitational lensing produces dramatic effects like the Einstein ring, a perfect circle of light. Through lensing, the universe itself becomes part of our observational toolkit, bending and amplifying light to let us see further back in time than even our best instruments could manage alone. Quasars, gamma-ray bursts, and gravitational lenses each tells us something unique. One shows us the slow, bright feeding of black holes. Another, the sudden deaths of massive stars. And the third, the invisible hand of gravity itself, shaping the path of photons. But together, they remind us of the central truth. Light is not just illumination, it is information. Every photon carries within it the record of an event, a journey, a cosmic condition. When we decode it, we are reading the autobiography of the universe. So join me in contemplating the grand narrative woven into the fabric of light. As we continue to explore the cosmos, remember that every flash, flare, and bend carries a piece of the universe's story, and we are the ones who get to read it. Light, the very essence of illumination, has been both a life source and a pathway to knowledge throughout human history. Yet despite its centrality in our lives and in shaping our understanding of the cosmos, the true nature of light continues to elude us. Even as we harness its power, the profound mysteries of light persist. The mystery of constant speed. The speed of light isn't just a random physical property. It's a cosmic speed limit, a barrier that nothing in the universe can breach. If you fire a gun on a moving train, the bullet won't travel faster than light. And even if the train is hurtling towards you at near light speed, your perception of the light from distant stars won't change. This baffling behavior of light led Einstein to revolutionize our concept of space and time with his theory of special relativity. According to his groundbreaking work, time isn't absolute, it's relative. An observer on Earth measures time differently from someone traveling at a high speed. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. It's as though time itself bends and stretches around light, ensuring it maintains its top speed no matter what. But here's the kicker. Why is the speed of light exactly 299,792 kilometers per second? That seems like an arbitrary number. Well, it turns out that this speed isn't just a fixed value. It's deeply entwined with the fundamental structure of our universe. You see, light is an electromagnetic wave, oscillating electric and magnetic fields that ripple through space. Its speed depends on two constants, the electric permittivity and magnetic permeability of free space. These constants dictate how easily electric and magnetic fields can change in a vacuum. By multiplying these two constants together, we get a value close to the speed of light squared. So the speed of light is a cosmic dance between electric and magnetic forces. It's a harmony that has remained constant since the birth of the universe. Could there be a death of light? Its photons, the particles that make up light, are considered elementary particles. They're the smallest possible chunks of light that can't be broken down any further. According to the standard model of particle physics, photons are massless and eternally free. However, there's a twist in the tale. While photons are incredibly stable, their mass could theoretically be slightly greater than zero. You might be thinking, who cares if they have a tiny mass? Wouldn't it be negligible? Well, it might seem negligible, but it would have profound implications. A non-zero photon mass means that photons are not immortal. They can't travel forever without losing energy. Over unimaginably vast stretches of time, photons could decay into other particles like neutrinos. Imagine the light from distant stars and galaxies gradually fading over billions of years. Not due to the expansion of the universe, but because photons are literally disintegrating. Such decay would be extremely rare, occurring after distances much longer than the age of the universe. But it opens up a Pandora's box of questions about the stability of light itself. Does every photon have a finite lifetime? So, how do we reconcile this with the constancy of the speed of light? These questions are not just academic exercises. They challenge the foundations of our understanding of the universe. Scientists are actively searching for signs of photon decay by studying the spectra of distant galaxies. Any deviation from the expected spectrum could hint at the immortality of light. Can we break the speed limit? One of the most enduring questions in physics is whether we can travel faster than light. After all, it seems like the ultimate frontier, the boundary of what's physically possible. If we could surpass this limit, it would open up a whole new realm of possibilities, allowing us to explore the universe in ways we never thought possible. But the short answer is no. We can't travel faster than light. It's just not possible, according to Einstein's theory of special relativity. The only thing that can travel at or faster than the speed of light is, well, light itself. As an object approaches the speed of light, its mass increases infinitely. That means it would take an infinite amount of energy to accelerate it to the speed of light, which is just not possible. So that rules out any hopes of building a spaceship that can reach light speed. But the story doesn't end there. There are some intriguing loopholes that physicists have explored. First, consider the concept of tachyons. Tachyons are hypothetical particles that always travel faster than light. They've never been observed, but they're mathematically possible within the framework of special relativity. The issue is that tachyons would need to have imaginary masses, which raises more questions than it answers. Another intriguing possibility is cosmic expansion. Space itself can expand faster than light, which means that distant galaxies recede from us faster than light speed. But that's not the same as traveling faster than light. It's more like riding on a wave. And finally, there's quantum entanglement. This bizarre phenomenon links to particles in such a way that measuring the state of one instantly affects the other no matter the distance. Some people claim that this spooky action at a distance, as Einstein called it, allows for faster-than-light communication, but it doesn't. The information needed to communicate something meaningful isn't actually carried by the entangled particles themselves. So while the mystery of light continues to baffle and intrigue us, we've come a long way in understanding its nature. From the constancy of its speed to its possible decay and the tantalizing prospects of superluminal travel, each facet of light reveals not just the elegance of the universe, but also the limits of our own understanding. As we continue to probe the depths of this celestial enigma, we're not just unraveling the secrets of light, we're refining our comprehension of the cosmos itself. Light is our greatest messenger, but it also carries with it some of the deepest mysteries of physics. We know how to measure it, we know how to use it, but when we ask the simplest questions, what exactly is light? Why does it behave the way it does? The answers lead us into some of the strangest and most unsettled corners of science. The speed of light, nature's cosmic speed limit. Perhaps the most astonishing fact about light is not just that it moves fast, but that its speed is absolute. In a vacuum, light always travels at 299,792 kilometers per second. It doesn't matter if the source is moving, if the observer is moving, or if the entire galaxy is rushing through space. Light's speed is always the same. This constancy is not intuitive. In everyday life, speeds add together. If you walk forward on a moving train, your velocity is the sum of your walking speed and the train's speed. But for light, no such rule applies. If a star moves toward us at a significant fraction of light speed and emits a photon, that photon still races away at the same universal limit. This peculiar fact is the foundation of Einstein's theory of relativity. Time, space, and simultaneity all shift to preserve the constancy of light speed. The faster you move, the slower your clock runs compared to a stationary observer length's contract. And simultaneity becomes relative. The reason the universe has a maximum speed limit, a cosmic speed of causality, is tied to the nature of light. But why this particular value? Why 299,792 kilometers per second? Physicists understand it as a consequence of the properties of the vacuum itself. Light is an electromagnetic wave, and its speed depends on the electric permittivity and magnetic permeability of free space. Yet the deeper why those constants have the values they do, remains one of physics' great unsolved puzzles. Does light live forever? A question of photon decay? We often treat photons as eternal travelers, streaming across billions of light years, without ever slowing down or disappearing. But does light itself have a lifespan? According to the standard model of particle physics, photons are massless and stable. A photon emitted from a star 13 billion years ago is identical to one emitted today. Yet some speculative theories suggest photons might not be truly massless, but instead possess a minuscule mass, so small it evades current experiments. If that were the case, photons might not be perfectly stable. It could, over incomprehensibly long timescales, decay into lighter particles, perhaps neutrinos, or as yet undiscovered components of the universe. Astronomers have searched for signs of this by studying the light from distant galaxies. If photons decayed, we might expect to see distortions in the spectrum, or a dimming that cannot be explained by distance alone. So far, we've followed light as a cosmic storyteller, carrying messages from the dawn of time. From black holes and collapsing stars, across billions of light years of expanding space. But light is not only a distant messenger. It is also the force that shapes our daily lives here on Earth. Without light, there would be no life, no climate, no technology, and no human civilization as we know it. Light is both the cosmic historian and the engine of our existence. Sunlight, the foundation of life every second. Our sun pours out 3.810 to the 26th power watts of power, an almost unimaginable flood of energy. Only a tiny fraction of that reaches Earth, but it is more than enough to sustain the entire biosphere. Through photosynthesis, plants and algae capture sunlight and convert it into chemical energy. This process produces not only the food that sustains nearly every food chain on Earth, but also the oxygen we breathe. In a very literal sense, every breath and every meal is powered by ancient sunlight. Sunlight also drives Earth's climate system. It warms the planet unevenly, creating winds, weather, and ocean currents. Seasonal cycles, rainfall, and even the growth of glaciers are all consequences of the interaction between sunlight and Earth's atmosphere. But light from the sun is not just a steady, nurturing source. It also carries hazards. High-energy ultraviolet radiation damages DNA, driving evolution but also causing mutations in skin cancer. The sun's flares and coronal mass ejections hurl bursts of energetic particles toward Earth, occasionally disrupting satellites and power grids. Life on Earth has evolved under this delicate balance, reliant on sunlight, but also shielded from its dangers by our atmosphere and magnetic field. Auroras. Light shows from solar storms. One of the most beautiful examples of light's interaction with Earth is the aurora, the shimmering curtains of green, red, and purple that dance near the polar skies. Auroras are born from the collision of light and magnetism. When charged particles from the solar wind stream toward Earth, they are guided by the planet's magnetic field into the upper atmosphere near the poles. There, they collide with oxygen and nitrogen atoms, exciting them to higher energy states. When these atoms release that energy, they emit visible light, painting the sky with waves of color. Auroras are not just a spectacle. They are a reminder of our planet's vulnerability. Intense solar storms can disrupt radio signals, GPS systems, and even entire power grids. In 1989, a geomagnetic storm knocked out electricity across Quebec for 9 hours. And in 1859, the so-called Carrington event triggered auroras as far south as the Caribbean and set telegraph lines on fire. These events show us that while sunlight is the engine of life, the sun's more violent emissions are forces humanity must learn to live with and prepare for. As our reliance on technology grows, light in human technology from the very beginning of civilization, humans have been fascinated by light, controlling it with fire, harnessing it with lenses, and bending it with mirrors. But in the modern age, light has become far more than illumination. It is the backbone of global communication and technology. Optical fibers. Nearly all of today's internet traffic, voice, video data, is transmitted as pulses of laser light through glass fibers. Single fiber, the thickness of a human hair, can carry terabits of data per second. Lasers. From medical surgery to barcode scanners, lasers have become ubiquitous. They rely on the precise control of photons to cut, measure, and transmit information. Imaging in medicine. X-rays, MRI scans, PET scans. Many of our most advanced tools for looking inside the human body rely on manipulating or detecting light in different forms. Solar power. By capturing photons and converting them directly into electricity. Photovoltaic cells allow us to turn sunlight into energy. Quantum communication. In cutting-edge labs, entangled photons are being used to develop unbreakable quantum encryption. Future where secure communication may be guaranteed by the laws of physics themselves. Light, once only a natural phenomenon, has become the foundation of the information age. Every video call, every satellite broadcast, every photograph on a smartphone, all depend on our ability to control and transmit light. The double roll of light from the sun's rays that nurtured the first life forms to the auroras that remind us of our planet's connection to the cosmos, to the fiber optic cables that link continents, and real-time light is woven into every aspect of Earth's story. It is not only our connection to the universe at large, it is the medium through which human civilization itself now operates. Light is both the message and the messenger, the foundation of biology and the backbone of technology. On Earth, we often take it for granted. But in truth, every photon around us, from a sunbeam to a laser pulse, is part of the same grand narrative that began with the first light after the Big Bang. Ultraviolet X-ray and gamma-ray astronomy. Seeing the extreme to study the most energetic phenomena in the universe, we need to look beyond the infrared. We must detect the shorter wavelengths of ultraviolet X-ray and gamma rays. These are the domains of the most violent events in astrophysics: exploding stars, collapsing black holes, and the birth of the heaviest elements. Such observations require specialized telescopes and detectors designed to withstand the extreme conditions and cosmic radiation of their upper atmosphere. High-altitude balloons, rockets, and satellites are the tools of choice here. The Chandra X-ray Observatory, for example, has revealed the supermassive black hole at the heart of the Milky Way and mapped the debris of exploded stars called supernova remnants. Meanwhile, the Fermi Gamma Ray Space Telescope has detected gamma-ray bursts, the most powerful explosions in the universe. Multi-wavelength astronomy, a universe in many colors today, astronomers rarely rely on a single telescope. Instead, they use observatories that span the entire electromagnetic spectrum. This approach has led to some stunning results. The Event Horizon Telescope, for example, captured the first image of a black hole's shadow in 2019. This was accomplished by combining data from 7 radio telescopes around the globe, each with a diameter of over 200 feet. The resulting image, a triumph of modern technology and international collaboration, showed the glowing ring of gas and dust around the supermassive black hole at the center of the Messier 87 galaxy. As our technology advances, the detail and scope of multi-wavelength astronomy will only grow. Future observatories like the Nancy Grace Roman Space Telescope will have the unprecedented ability to observe the infrared sky in a wide field of view. This will allow for things like characterizing exoplanet atmospheres and probing the mysterious dark energy that is accelerating the expansion of the universe. The quest to understand our place in the cosmos is a journey across the entire electromagnetic spectrum. It is a testament to human ingenuity that we have built instruments to capture the universe's faint whispers and its explosive roars. And as we continue to reach new frontiers in astronomy, we can be sure that our view of the cosmos will continue to expand. What's more, astronomers are now discovering ways to actually hear the music of the spheres. Listen closely. Do you hear it? The low hum of a star being born, the crashing symphony of a supernova, the eerie song of a black hole. All these sounds and more are part of the rich soundscape of the cosmos. In every direction, 100 billion stars, each with hundreds of billions of planets. Our galaxy is vast, but it's only one of many. Across the universe, other galaxies also swirl with stars and planets, and both smaller and larger things. Some are close enough for us to see their individual stars. Others are so distant that they appear as only a smudge on the sky. But we can still make out some details by looking at different kinds of light. At one end of the spectrum, there's radio. This is where we find the cold hydrogen clouds where stars are born. Then comes visible light. That's what our eyes detect, and it dominates the night sky with the twinkles of stars and the glows of nebulae. A bit of both combine in the infrared, revealing the warmer dust where new stars are forming. Here, starlight filters through gas and leaves behind the red glow of scattered light. And then there's the ultraviolet, where stars shine as they burn bright and hot in their youth. As they age, they cool down and become more of a red glow in the infrared. But it's what's left that often reveals the true nature of a celestial object. If it's massive enough, a star will end its life in a supernova explosion, briefly shining in X-rays and gamma rays. These wavelengths don't reach Earth's surface, but orbiting telescopes can see them. An example is NASA's Chandra X-ray Observatory, which launched in 1999. It shows us the violent side of the universe, like the remnant of a supernova that occurred about 290 years ago. Visible light can't penetrate the gas cloud, but Chandra's X-rays can, revealing what lies within. We see a glowing loop of material that once was part of the star's outer envelope. There's also a smaller inner bubble, where the star's core exploded, leaving behind a rapidly spinning neutron star. These dead stars, if massive, can also be seen by the Fermi Gamma Ray Space Telescope. When matter is converted into antimatter, it releases a burst of gamma rays. These flashes can briefly outshine an entire galaxy. They're called gamma ray bursts, and the most powerful ones are among the universe's rarest events. Yet Fermi has detected about one every day since it launched in 2008. It has also revealed a steady glow coming from nearly every corner of the galaxy, diffuse haze of gamma rays. This haze may come from the same sources that fill the universe with radio waves, the remnants of the Big Bang. These ancient particles could be interacting with the cosmic microwave background. The afterglow of the Big Bang. Studying this interaction might help answer the question of what the universe is made of. Gamma rays may even reveal the elusive dark matter if it interacts with normal matter. The signal is faint, though, and hard to detect above the noise of the universe. To solve this problem, scientists are building a next-generation gamma ray telescope on Earth's surface. CTA will be 50 times more sensitive than Fermi. This will allow astronomers to peer deep into the heart of galaxies and look for signs of dark matter. Meanwhile, another major project is under construction in Chile. Its 4-mile-wide array of radio telescopes will survey the entire southern sky in exquisite detail, searching for everything from pulsars to planets. Over the decades, this new generation of instruments will continue to fill in the gaps in our knowledge, and each new discovery will inspire new questions and new ways of looking at the cosmos. Soon, our picture of the universe will be complete. We'll be able to look back through time and see the universe as it was born. Maybe we'll find that we're not alone. From the tiniest microbes to the largest galaxies, the world is full of patterns at every scale. As we explore deeper and deeper into space and time, we find echoes of ourselves everywhere around us. Keep finding ourselves reflected in the rhythms of the cosmos, which are written in light. And now we have the tools to read them. Our journey began when we learned to see the universe in visible light. Continues as we explore wavelengths beyond our perception. Every new wavelength reveals something new. And now we beginning to understand that seeing the universe in just one wavelength is like listening to music with only one note. Only by combining all the notes, all the frequencies, do we get the full picture. Only by combining all the wavelengths, all the colors, do we hear the full symphony of creation. Light is the key to the universe. It's how we see. It's how we learn about the world around us. It's how we study the entire cosmos. If not for light, we would be utterly lost. So let's talk about light, because today, light takes us on an epic journey from the dawn of time to the death of the cosmos. In the latest episode of C-Show Space, we have followed light from its first appearance in the early universe through the blazing fires of stars, the beacons of quasars, the flares of gamma ray bursts, and the subtle bending of gravitational lenses. We have traced it through Earth's skies, our technologies, and the instruments we have built to capture it.
But
The story of light is not finished. It points us toward the future, both our search for life beyond Earth and the ultimate fate of the cosmos itself. When a planet passes in front of its star, some of the starlight filters through its atmosphere. By analyzing that light with spectroscopy, astronomers can detect the chemical fingerprints of gases like oxygen, or methane, or water vapor. These are potential biosignatures, hints that life might be present. This technique has already been used to study the atmospheres of large exoplanets. Future telescopes, such as the planned Habitable Worlds Observatory and massive ground-based telescopes like the Extremely Large Telescope in Chile, will push these studies further, examining Earth-sized worlds in the habitable zones of their stars. Even now, the James Webb Space Telescope has begun analyzing the atmospheres of distant planets, searching for signs of chemistry that cannot be explained by geology alone. One day, photon captured by our instruments may carry the first evidence of alien biology, the most transformative discovery in human history. But while we look for life elsewhere, we must also confront the distant future. Light itself will write the final chapter of cosmic history. The stars we see now are temporary. In a few trillion years, nearly all will have burned out, leaving behind white dwarfs, neutron stars, and black holes. Galaxies will grow darker, star formation will cease, and the universe will drift into a slow twilight. Over unimaginably long timescales, even black holes will evaporate through Hawking radiation, releasing their final photons before vanishing. In this far future, the cosmos will be vast, cold, and nearly empty. The last photons stretched into radio waves by the expansion of space will fade into the background. Light, which once blazed across the skies, will become a rare and dying whisper. the universe will enter what physicists call the heat death, a state of maximum entropy where no new structures can form and no new light will shine. So in many ways, our current era is a golden age for light. There has never been a time like the present when so much knowledge is available to us. Astronomers are constantly making new discoveries about the universe thanks to increasingly powerful telescopes, and we are just getting started. Breakthroughs in computing power are allowing researchers to model and analyze data from these telescopes in ever greater detail. Someday soon, they hope they will detect the first signs of life elsewhere in the cosmos. It wasn't always this way. The earliest humans didn't know what light was, only that they could see. They saw shadows moving across cave walls, heard the music of birds at dawn, watched the northern lights dance across the night sky. But they couldn't know that those experiences were caused by photons bouncing off of solid objects or passing through our atmosphere. The idea of light as a physical phenomenon remained shrouded in mystery until the scientific revolution in the 17th century. Then scientists began to unravel the nature of light and the universe itself. They learned that visible light is just a small slice of the electromagnetic spectrum. Beyond the frequencies we can see lie radio waves, microwaves, X-rays, and gamma rays. And it turned out that the universe is filled with all kinds of light that we can't see. Radio telescopes reveal the universe buzzing with signals from distant galaxies. With each new wavelength we have explored, we have gained a deeper understanding of the cosmos. And in doing so, we have learned more about ourselves. For example, we know that life on Earth depends on liquid water. But water doesn't just exist here. Comets, asteroids, and other bodies throughout the solar system have ice. That suggests that the ingredients for life may be widespread in space. And since water absorbs visible light, but reflects infrared, we can use special cameras to detect it on other worlds. The first such discovery was made in 2015 when researchers found evidence of water on Mars. Now astronomers are using similar techniques to hunt for water and other signs of life on planets orbiting distant stars. Water isn't the only thing we can look for. Given enough technology, we can develop instruments sensitive enough to detect the heat signatures of planets. It's giving us clues as to whether they have an atmosphere, and if so, what it is made of. To do this, scientists are building an incredibly advanced telescope called the Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s. The Roman telescope will be able to measure tiny changes in the brightness of stars as planets pass in front of them. Then using infrared light, it will detect the heat signature of those planets. This method will allow the telescope to study the atmospheres of rocky worlds, roughly the size of Earth. Already scientists are planning follow-up missions to study the findings of the Roman telescope. The first observations from these next-generation instruments will revolutionize our understanding of exoplanets, and they will be the first step in the search for life beyond Earth. If we find it, there is little doubt that the news will spread quickly around the globe. But how should we tell the rest of the universe? That will require a new kind of communication, one that harnesses the power of light itself. For centuries, humans have dreamed of talking to aliens. Science fiction has been full of imaginative ways that we might make contact, from giant radio beacons to handheld communicators. But the reality is likely to be more subtle. The first alien species we encounter may not even be broadcasting its presence. Instead, we will have to look for signs of technology. Some experts believe that aliens might build enormous structures on their planets that could be seen with powerful telescopes. Others think that they might release huge amounts of light into space, either intentionally or accidentally. Either way, finding evidence of aliens will be only the beginning. We will then need to figure out how to communicate with them. This won't be easy. Even if we assume that aliens are intelligent enough to understand our messages, the distances between stars are so great that communication will be slow. The nearest stars are more than 4 light years away. So it would take 4 years for a message to reach them, and another 4 years for a response to arrive. But with the right technology, we could send messages back and forth faster than that. By harnessing the power of light itself, we could send laser beams across the galaxy, carrying with them the story of humanity. As we look up at the night sky, it's easy to get lost in the beauty of the stars. They twinkle and shimmer, creating a sense of wonder that has inspired humans for centuries. But what exactly makes stars shine? Stars are giant balls of gas that generate energy by fusing hydrogen into helium. This process releases enormous amounts of light and heat, which is why stars are often called furnaces in the sky. Light travels in waves, and the color of a star tells us how hot it is. Hotter stars emit more energy and appear bluer. Cooler stars emit less energy and appear redder. The brightest stars in the sky are the closest to us. The farther away a star is, the dimmer it appears. This is why we use apparent magnitude to measure the brightness of stars. Apparent magnitude is a logarithmic scale that ranges from 1 to 30. The brighter a star appears, the lower its apparent magnitude. The brightest stars in the sky have apparent magnitudes of about 0. The faintest stars that can be seen with the naked have apparent magnitudes of about 6. The size of a star is measured in terms of its radius. The largest stars in the universe are hundreds of thousands of kilometers in diameter. The smallest stars are only slightly larger than Earth. The mass of a star is measured in terms of its luminosity. The most massive stars are millions of times more massive than the Sun. The least massive stars are about the same mass as Jupiter. Stars come in a variety of shapes and sizes. Most stars are spherical, but some are shaped like disks. Stars can also rotate, and some have strong magnetic fields. These fields can cause the star's surface to glow brightly in certain areas, creating sunspots. Stars produce light through nuclear fusion. This is the process of combining atomic nuclei to form heavier nuclei. In the case of the Sun, the most common type of nuclear fusion is the conversion of hydrogen to helium. This process releases tremendous amounts of energy in the form of light and heat. Now, as we stand on the verge of discovering life elsewhere in the cosmos, it's important to remember that we are just one part of a much larger story. Light is the key to the universe. It's how we see. It's how we learn about the world around us. It's how we study the entire cosmos. If not for light, we would be utterly lost. But as we continue to explore the universe and search for life beyond Earth, we must also remember that we are not alone. The universe is filled with wonder and beauty, and we are just beginning to understand it. As we look up at the night sky, let us marvel at the incredible power of light and the amazing discoveries that await us. I hope you enjoyed this Sea Show Space episode. If you did, please subscribe to the channel so you don't miss any future episodes. Thanks for watching.